Good afternoon, everybody, and thank you for joining us today. We're the Null Space Invaders, and we're excited to share a project titled Kalman Filters Navigating the Future of Autonomous Vehicles. This topic sits at the intersection of advanced mathematics, real time data processing, and the future of mobility, and we've honestly had a great time, so let's dive into it together. Let me first introduce the team. My name is Omar Kader. I'm a computer science major. We also have Eric Bufalino, who's also a computer science major with a minor in physics. We have Michael Monday and Bahrouz Mohammadiev are both computer science majors. Ahmed Abdul Hamid, who's pursuing an industrial engineering bachelor, and his insights into optimizing and systems flow have been crucial for practical applications. We're also joined by Fandi Cruz and Mustafa Ismail, whose contributions have helped us ground our research in real world use cases and also bring a broader perspective to the project. Together, we've investigated how Kalman filters play a vital role in helping autonomous vehicles navigate in environments where they get noisy sensor data and how they make accurate and real time navigation decisions. We're looking forward to walking you through what we learned, so let's dive in.
Hi everyone, today we will be delving into a powerful tool that helps autonomous engineering systems called common filters and how linear algebra plays a key role in making them work. Let's set the stage with a real world problem. GPSs aren't perfect. They oftentimes fail in tunnels or urban areas that are dense with tall buildings, known as urban canyons, or even get jammed altogether. So here's the big question: how can self driving cars stay on the track without GPS? That's where common filters come in. They're designated to help systems make smart decisions even when the sensor's data is messy or incomplete. In this presentation, you will learn what a common filter is, how it handles noisy sensor data, why it's important for autonomous navigation, and how linear algebra is the engine behind it all. On the right side of the slide, you will see a simple diagram of how the common filter works. The system will start with a state, then it makes an estimate. It updates the estimate with sensor measurements using something called a common gain to get a more accurate picture of reality. By the end of this talk, you'll see how all of this ties together to help machines understand and navigate the world, even when the data isn't perfect.
My name is Eric Buffalino, and let's talk about the core of the issue we're tackling today. How can a self-driving car accurately determine its position using noisy GPS or sensor data? In the real world, these autonomous vehicles use things like GPS, IMUs, and LiDAR. GPS can be distorted when tunnels or dense cities. Inertial measurement units, or IMUs, have short-term motion tracking, but small errors can add up over time. And LiDAR uses lasers, which are very accurate, but can be distorted with weather or reflective surfaces. While all these sensors are powerful, how do we corroborate them all together when all of their data can be potentially flawed or distorted due to outside factors? That is the challenge we face. How do we make reliable decisions when the data you're getting is flawed? This is where Kalman filters come in.
Before we dissect why self-driving cars can rely on Kalman filters, I kind of want to discuss why we can't just rely on something like GPS. Basically, you may notice when you use your iPhone or whatever phone you have, GPS isn't the most accurate reading in the world, and this can be further amplified if you were in like a city environment or like anywhere with heavy traffic. The signal can go out; it can just get all crazy. So what the Kalman filter will do basically is it'll use linear algebra and other methods to combine data around you and then give you more fast, quicker, accurate readings that just completely blows GPS out of the water.
So, what is Kalman filter? At a high level, it's a way to make really good guesses when your data isn't perfect, which, let's be honest, is most of the time. Imagine you're trying to track a moving car using GPS, but the signal is a bit off or it jumps around. The Kalman filter helps smooth that out. That it works by cycling through four steps: predict, measure, update, and repeat. First, it makes a prediction based on how things have been moving so far, then it checks that against new real world data like a GPS reading. It compares the two, figures out how off it was, and adjusts. And then it just keeps doing that over and over. What's powerful about it is that it doesn't throw out old info and it doesn't blindly trust new info. It blends both to give a better estimate. It's used in everything from self-driving cars to drones and even finance. It was developed by Rudolf Kalman in 1960, and even today it's kind of the gold standard for filtering out noise and making smart predictions.
Why do we need Kalman filters? Have you ever wondered why Kalman filters are so important in modern tech? So the devices like GPS, gyroscopes, and accelerometers are everywhere, but they're not perfect. You can use them, but they're not the best. They not only that they're noisy, they're unreliable, and there's some sort of interference that happens around. Most systems today have to work in real time, so this is where Kalman filters come in. They're brilliant at reducing measurement noise, combining data from multiple sensors, and predicting future states like position or speed. If you look at the graph on that page, figure 1, Kalman filter smoothing noisy position and velocity measurements. The value in blue are recovered from noisy observation, which is in red, through estimated trajectories. Um, so when Kalman filters, they help recover the true signals, so whether it's for self-driving cars, drones, or navigation system, Kalman filters are the secret behind smooth, smart, and reliable performance.
Alright, so on this slide, we have the mathematical foundations that are used for the Kalman filter, basically. We want to start off with the state vector, which is the base for all this, basically. It represents position and velocity. It works in tandem with the state transition matrix, which basically projects how fast you're going and where you'll be within the next few moments, and it'll keep on, so on, so on. Right after that, we have the observation matrix, which is basically what we're measuring, kind of like GPS, I would say, and it kind of just reads what the sensors are saying and trying to dissect that. And then there's some matrix multiplications that are super important. The prediction step, which essentially works with the state transition matrix much more closely compared to the other ones. Convariance update, which is basically uncertainty, and the Kalman gain, which just computes the balance of trust and prediction with the actual measurement of everything. So
the Kalman filter takes a bunch of noisy guesses and makes one smart decision. It works in 3 steps pretty much. Step 1 is predict. Even without a GPS signal, the Kalman filter uses a motion model, like the car speed, direction, and acceleration, to predict where the car should be next. That's step 1. Step 2 is measure. Let's say the car finally gets a GPS reading, but it's a bad one, maybe off by 5 meters. The filter recognizes that this GPS is reading is wrong and gives it less weight, using something called the measurement noise matrix. And then step 3 is update. Now the filter blends its prediction with the noisy GPS reading using the Kalman gain. If the GPS is very unreliable, the filter trusts its prediction more instead of the car making a wild jump based on a bad GPS point. It smoothly adjusts using both the motion model and the sensor input. So this is pretty much what the whole the use of the Kalman.
In conclusion, why are Kalman filters so important? So first of all, it's a very reliable form of navigation. So Kalman filters allow self-driving cars to maintain accurate position even with noisy or missing data, and that's powered by the mathematical systems. So linear algebra enables real-time predictions and corrections using state vectors and matrix operations. And our third point is going to be sensor fusion. So by intelligently combining data from GPS, IMUs, and other sensors, Kalman filters boost both safety and efficiency. And our last point is going to be future ready. So we see it right now, self-driving cars are everywhere, and that's thanks to Kalman filters, because that's going to be a cornerstone for intelligent navigation and error reduction in the future. Thank you.